Hi, my name is Steph Evans and I'm the lead FEA engineer at Evotech CAE Limited. This video, presented in collaboration with MSC Software, makes up a tutorial from the Apex 101 for Aerospace Applications series and is focused on a number of aspects of idealization and mesh development within Apex. We're using the Harris Hawk release, highlighting key functionality using the geometry, mesh and associated tools. In this worked example, we'll go through the full model development for a typical aerospace component, in this case a leading edge rib. This will be focused on a number of different idealization and modeling strategies depending on the overall intention of the model. This will take CAD source description of the rib and look at various FEA representations from a simple loads model through to a 3D stress model with ultra rapid model development for different levels of idealization. So through the worked example we'll look at 4 key stages. Stage 1, stiffness and load path model. So that will include the idealization of a loads level model looking at a leading edge rib with 1D beam elements, rib flanges and stiffeners, and a 2D shell element definition for the rib webs. And this is typically used for stiffness and load path assessment in a coarse full aircraft global FEA model. Stage 2 will then involve a joint and stiffener detailed model using 2D elements, and this will include a fully mid-surface definition of a rib with 2D shell elements for ribs, rib flanges, stiffeners and webs, typically used for joint fastener load extraction and stability assessment in integrated subassembly FEA models. Thirdly, we'll look at a detailed stress model with 3D TET elements, and this will include a solid model definition of a rib with 3D tetrahedral elements used for complex geometry and detailed features. And again, this is typically used for a converged stress output in detailed component FEA models. And then finally we'll look at some hybrid modelling techniques including the use of 3D hex elements, and this is based on a highly efficient 3D hexahedral rib feature modelling or set of modelling techniques used as a standalone mesh type or as a hybrid approach in conjunction with 3D tetrahedral and or 2D shell models, and this is typically used again for converged stress output in detailed component FEA models where a reduction in model size and solve time is required. So looking at the first level of idealization, so we're going to build a loads level model using 2D shell and 1D beam elements. So we've got some rib, a rib geometry in the Apex environment, and we can see this is typical of a standard type of aerospace component, so lots of thin webs, thin surfaces, fastener holes where the assembly will be connected to residual structure, stiffeners and lightning holes, again thin, more lightweight structure. So we're going to start the idealization by mid-surfacing the rib structure using the incremental mid-surface tool, and this will work its way through the geometry and pick out the associated pairs that it wishes to develop mid-surfaces from. So you can see the colour coding for paired faces, so either face of a solid region, and we're going to edit those mid-surface pairs. You can see around the nose of the rib, we're going to join those together, so we've got a single blue mid-surface for the region shown, and once we're happy with those pairs we can select all the mid-surface definition and create the mid-surfaces accordingly. So we can see now the surfaces, and if you look in the model browser tree we have a set of unique surfaces created. Some of them are not connected at this stage, so if we auto color we can see the discrete definition, and if we turn on edge visibility we can see there's lots of red edges, so they're disconnected from one another. So some initial manipulation or idealization of the geometry, so we're removing some of the local features, local detail, and then simply extending surface edges to bring them into position as per our local idealization. So you'll see there's a gap in the joggle region, as it's known, at the top of the rib, a gap of about 40 millimeters. So with that in mind we're going to look at the extend surface functionality and put an extend surface distance of 45, so greater than 40. Select all the surfaces and the middle mouse button to accept, and we can see we now have a general body or general surface defined in the model browser tree, so by and large everything is connected together as required. So some local manual edits, again using the vertex edge drags tools, very powerful with the direct modeling functionality in Apex. You can see some of the idealization that's happened just from the plane mid-surfacing. So we're into a situation where we can use some of the auto and manual tools to update accordingly. So we're just now going to delete all of the flange and stiffener definitions for this particular example, the loads model. All of the model, or all of the mesh rather, is going to lie in the plane of the original mid-surface of the rib as shown on screen now. So we've got the plane surface definition set up, and we have the curves in place that represent the local flange and stiffener detail, as you can see with the sort of zigzag line across the surface there. So some local edits: remove unnecessary vertices to simplify the structure for resultant meshing, and then we just take a typical 25mm element edge length, mesh using the default mixed tri and quad with auto algorithm turned on, and the mesh is generated very quickly and pretty good definition based on that element edge length. So just some local updates. So we're defeaturing around some of the lightning holes. You can see that the geometry is updated, and the generative nature of Apex again updates the underlying mesh. So we're not into continual back and forth geometry mesh updates. Checking the surface normals. So first of all, checking for surface consistency. So we can see all the normals are pointing in one particular direction. We actually want the normals to point in a different direction based on the output quantities that will be developed for the model. So simple check and then update to give us the orientation definition that we want. Okay, so with the 2D mesh controlled or defined and controlled, we're now into curve meshing. So we could enter an element edge length, but because we're meshing the edges and internal curves of the underlying rib surface, then it will take the 25mm underlying edge length accordingly. So it's just a case of a sweep pick to pick all the curves, obviously remove the curves from the lightning holes that we don't want, and we can see the curve mesh generated on screen. And the because the mesh, the 1D mesh was developed from the 2D surface geometry, then everything is equivalent. So a quick check on element quality, and we can see that we have got a number of poorly shaped elements in a particular region, so we can use the fringe plot to highlight those regions, and then it's just a simple case of using the vertex edge drag to tidy up the areas where we have problem element shapes. Again, very powerful with vertex edge drag. So mesh is now complete. Looking at some of the underlying CAD definition in terms of the rib and stiffener definitions or geometry, going into wireframe mode or transparent mode for the CAD definition, we can see how the flanges will sit against the underlying mesh topology. So we're putting some vertex or hard points into the mesh to give us a transition where we can see the rib flange spreading outwards. So we're going to define a series of different 1D beam properties to give us the idealized 1D beam stiffness that we require. So making some measurements across the width of the flanges. So we've got 127 and 177 for a different dimension, and then 15mm thick. So with that in mind, we can go into the beam attribution tool, and we're going to define our sections first of all. So pick rectangular section, put the span name in as it, the shape name in, as it calls it in Apex. So rectangular section, we're using a naming convention where we know the dimension from the name. So 127 by 15 millimeters, and then the second one 177 again by 15. So 152 by 15, I should say, which is the mid section for the transition in the flange widths. So putting those parameters in, and then a third shape again 177 by 15 based on the measurement for the CAD geometry. So putting that in again, and we've got our three beam sections which we need to apply to this model. So once we've got the shapes defined, we go into what Apex calls the spans. So this is effectively linking the shape to the region of the model where the shape will be applied. So again, using the span names similar to the shape names, so picking the span and then the underlying geometry, picking the position where we want the span to be applied in the model, and we can see a very quick 3D update into the display to show how that span looks compared with the rest of the model. And again, doing this for the midsection, so 152 by 15, assigning that to the next curve within the shell plane, and again a second midsection, or rather second beam span 3D display is shown, and then finally the 177 by 15 for the widest geometry in the region, and again applying that to or assigning that span to the model, and we can see the offset, rather the 3D display shown accordingly. So if you compare that with the underlying CAD definition, we can see that there's that there are no offsets defined on the spans at the moment. So we can double click on the span from the browser tree and then invoke the triad by simply clicking on the vectors, and then we can pull or type in the offset values that we want to use. If we had the 3D CAD display on, we could do this by eye, but of course because we know our section dimensions, we can define those offsets explicitly. So putting in the half width or half flange width to shift the flanges over, given the single-sided rib construction, and repeat that for all three sections. Offsets very easy to define, and we can either input these directly into the table, the span table as shown on screen, or we can modify the triad accordingly. And again, very quick to create, visualize, and then manipulate the 1D geometry as required. So we can put the 3D geometry on and show that we've got an excellent representation of that transition in terms of the flange geometry. So with those typical dimensions defined, we can work our way around the model. Just save some of the mouse clicks here, but we can see in the browser tree all of the regions defined and color coded, and then shown with the underlying CAD shown in view as well. So we can make a very good assessment, or a quick assessment of how the structures are looking. We've idealized in the joggle regions, so there's a little bit of difference between the CAD and the idealized FEA representation, but that's something that would be captured in the next level modeling, which we'll talk about in a moment. So we can run the model if we've just got a simple sort of outplane bending case here, and we can look at beam outputs. So that's shown stresses, beam stresses, or force and moment for the beam, and similarly for shells. So we've got effectively a 3D display of the output for a given model type. So second approach. Now this is the 2D representation that will be used for a joint load definition or stability assessment for this type of structure. So again, exactly the same CAD geometry, similar technique to start off with, in the fact that we're going to use the incremental mid-surface tool to pick out paired surfaces, or paired external surfaces, or paired faces I should say, to generate the mid-surfaces. And again, happy with those pairs, select the pairs to create the underlying parent geometry, and we can turn the CAD off and show the surfaces as required. And again, color coding, or using the auto color to display the discrete types. And we can see that there's a region where the incremental mid-surface has not quite captured the surfaces as required. So easy to fix. We just go in and use the automatic mid-surface tool. So pick a face, middle mouse button to accept, and it projects the thickness through, and then gives us a surface at the true mid-surface for that region. And again, if we turn the CAD geometry off, we can see those two new surfaces created. So create some filler surfaces just to effectively join the edges up and tie the structure together, and then we can use the auto extend, where we extend surfaces based on, in this case, the default search distance So picking all the edges, or surfaces rather, and it's going to project all the edges and snap everything together. And we can see in the model browser tree that there's a single mid-surface created. Changing the colour just to make visibility a bit easier. So we can see the free, shared and manifold edges along with the vertices shown. So it's overestimated or over-projected some of the surfaces in this region. So it's in the case of just going in and deleting those surfaces which we don't need, and repeating that for various parts of the model. Again, vertex edge drag coupled with the direct modelling tools makes it very easy. We're not back and forth into various forms. This is basically done all off the mouse, so mouse to select and middle mouse button to accept. So we don't need lots of form access or lots of keyboard shortcuts, that type of thing. So it keeps the user interface very clean and equally very quick to perform operations of this nature. So we can look around the structure, and again, from the geometry perspective, it looks like we're relatively happy with the idealization in terms of the mid-surfaces. So now we'll get into surface meshing, again using the mixed tri and quad with the appropriate element edge length, 12.5mm in this case. Mesh those quickly. We've got the feature mesh settings turned on such that we get good control over say a ring of elements around the hole and that type of thing. So checking the element quality, we've got some let's have a look. Yeah, we've got some poor elements, or rather some invalid elements at one particular location. So just isolating those elements and growing the mesh so we can see where the problem elements are, and we can use vertex edge drag to snap vertices together, and again those element definitions are improved, and we can just delete the overhanging piece of geometry as required. And again, looking in the element quality fringe plot, so we've got no invalid elements, one bad element, and the rest are dominated by good quality elements. So a check on surface normal consistency, again colour coding the upper and lower face of the shell element, so we can see they're pointing in a direction, well, so some of the areas are pointing in a direction we're perhaps not happy with in terms of consistency. So we're just going to pick an element in that given meshed region, and it will automatically flip the connected shells to suit. So we can now see we've got the shell normals, shell normals consistent first of all, and then the orientation is highlighted as a vector plot, so we can demonstrate that we're happy with that. So very quick to mid-surface shell mesh, and then surface normal updates and what have you. So we're looking at element topology, similar to the geometric free, shared and manifold edges. We can look at that on a mesh basis, but so we've taken the geometry out of view, and we can see we're happy with the topology in terms of what's connected as appropriate. Okay, so some simple defeaturing. So if you notice, we've got lots of holes at the fasteners position from the underlying CAD definition. So we just selected the geometry, and then we're going to defeature 2D holes and create a seed point at the centre of the defeatured hole. Select the mid-surface topology, middle mouse button to accept, and we've got a series of hard points defined at the fastener centres. So geometry update and mesh update in a blink of an eye, really. It's trivial to do this stuff in Apex these days. So again, turn the hard points red so we can just see where those hard points are defined. And again, using the 12mm element edge length, you can see we've got lots of elements between subsequent fastener definitions. It's missed one of those defeaturing holes by virtue of the fact that it probably doesn't see it as a circular hole on that curved face, but we can just go in quickly and just manually defeature that and create the hard node seed point at the centre of the hole. So that gives us the mesh definition to get us going, but then we want some perhaps some better element quality around the fastener definition. So we're going to redefine the mesh with a mapped mesh algorithm, so we can see we've got a much cleaner definition around the flanges. So we've got nice regular squares at all the fastener positions. and then we perhaps might go back to the auto mixed tri and quad paved mesh for the underlying regions, just to get some local mesh uniformity where we don't have discrete fastener or hardpoint definitions. So that's the mesh completed. So once we've got that, we can look at element properties. So of course we need to define the 2D thickness for each of these mesh regions. So we're going to use the auto thickness tool, so that enables us to pick the underlying mid surfaces, and then pick the master CAD geometry, if you like, that was used to create those surfaces in the first instance. And then we can see the thicknesses, both in terms of thickness and offset that Apex has computed from the underlying CAD definition. And we can see, if we look at the joggle region down here, it's made a good attempt, but the joggle thickness has thrown a bit of a wobbler in terms of the local thickness attribution at these points. So we can just once we've been through the model, we can go back into the section tools and update the thicknesses accordingly. And again, you can see at the nose of the rib there was a slight inconsistency between adjacent meshed regions. So going to section view, and this then gives us sections on a color-coded basis. So it's very easy to determine which areas of the model we need to modify and update based on the underlying property. So we can see here at this joggle region, we're going to use the blue area as a master definition for one of the step surfaces. Again, we can look at the 3D thickness profile and see that's updated nicely as we require. And again, for the purple region, if you like, we can assign that property set to the next step surface in the region, and again repeat that for the various areas where we have potential issues. And again, in this lower joggle region, we can see where the thickness was massively overegged by virtue of the underlying CAD definition. We're going to match up the joggle with the sort of yellowy brown surface, and then define that on the step joggle surface. Again, trivial to highlight, update, and yeah, we can see the 3D geometry, or rather the 2D thickness is updated as we require for those updated regions. So finally, we've just got a region on the nose of the rib. We're just going to map those, or rather assign those thicknesses across again, just picking an individual face of the surface, and again the properties are updated as we require, so we can switch back to 3D mode to double check that if necessary. And again, yeah, so we've got a range of maximum of about 31mm. So yeah, a very good representation of the underlying CAD definition, and very quick to give us those property sets that we need. So moving on to model verification, or rather running some loads through the model just to understand how the model is going to work. So this level model would probably be tied into a sub-assembly through the use of some idealized fasteners, maybe a discrete node-to-node fastener or some kind of shared load transfer fastener, but in this case the fasteners are all defined at these hard points. So we're going to simply define a boundary condition on those hard points, and then run some pressure loading through the rib webs to give us an out of plane bending action, and then understand what that does in terms of the load transfer through the fasteners. Of course, this is for example purposes, but yeah, built into a larger assembly, we'd be pulling again the idealized fastener loads maybe through a C-bar type element, or C-bush flexible bush type element to understand the load transfer through a given joint. So load and boundary conditions set up, run through the loads and boundary conditions, check, model verification check, and then setting up the analysis. So we're going to run a buckling analysis in this case, so pretty quick to run through. Just while that's running, we can see that in the bottom left hand corner, all of the model or the analysis updates that are going through. So again, this is pretty quick to do this. It's not quite real time, but you can see obviously for a model of this level, You don't want to be getting into an external export and then solve just to understand if your model's been held together correctly. So for this linear buckling analysis, which is now completed, so it runs through the eigenvalue extraction to give us our buckling factors, and then look into the post-processing side of Apex, and we can see we've got our buckling modes with our load factor, so significant load factor required to buckle, but we can see the outer plane pressure load would buckle one of these shell ribs at the buckling factor 7 as shown on screen, and then we can look at things like the displacement, stress if necessary. Of course that doesn't make too much sense for an eigenvalue buckling analysis, but we can look through the model response based on our local and global buckling modes and understand what the structure is doing. And then we're just double checking the constraint reaction forces, but imagine this was built into a larger assembly. We see these as discrete fastener loads coming through for this type of structure and this type of analysis. Again, so a level of idealization which gives us more insight into the rib. So perhaps some more work to set this up, more work to develop the geometry, mesh, and properties, but an order of magnitude more detailed in terms of the model output compared with the original loads level model that we looked at with the 1D and 2D definition. So moving on to the next stage 3, or the third model type. So what we're interested in now perhaps could be some detailed stress outputs. Maybe we're interested in the fatigue life of this component, so we want ideally converged stresses shown, or rather displayed for this type of model. So we're into the solid mesh definition, so tetrahedral elements with mid-side nodes, so 10 element type, 10 nodes in total per element, running through the meshing algorithm. So we're using again a 12mm element edge length turned on, and we can see the mesh develop very quickly, tetrahedral, so it fills complex geometry with basically no user input in terms of geometry cleanup or tidy, anything like that. In this example we're looking at element quality, so if we did have maybe sliver surfaces or that type of thing, they'd be shown up in the mesh check. But we can see here that there are some bad elements potentially in this region of interest that we might be interested in, but generally speaking we've got good quality elements in there. So once we've done the initial model check, we can use some of the controls on the 3D mesh. So we might wish to have local controls on fillets, chamfers, cylinders, etc. But in this case we're going to look at the defaults except for the washers. So that creates, or gives us the ability to create a ring of elements around a fastener hole, useful for loads of boundary condition definition potentially, or results extraction from these given regions. So we've got a larger lightning hole, and then we've got much smaller holes at the fastener interfaces. So we're going to edit or control the feature mesh settings such that we've got features or holes with a radius of less than 40mm, where the feature mesh settings will be active, whereas for the larger lightning hole those features will not be active, so we don't need to worry about them. So again, we can see we've got all the features turned on. We can turn discrete ones on and off as required, but in this case we want control over the hole as an example, and also the fillets in this joggled feature within the rib where we have double curvature in terms of the fillet definition, which may be an issue in terms of crack propagation. And again, you can see, so we've got a ring of elements around the fastener, and we've got the good control over the feature, the fillet features in that particular region. And again, you can see around the lightning hole we don't have a ring of elements, but we're not particularly concerned about that, given how we've controlled the feature mesh settings for the overall rib definition, rib mesh definition. So we could get into a scenario now where we might wish to locally manipulate the mesh definition so we've got more elements and more detail in a given region of interest. So we're going to look at some ways of splitting the underlying geometry. So we've got some construction geometry developed, and this is going to be used to break the underlying rib 3D geometry into some discrete parts. So we've got a couple of ways of splitting. We can split with a face or a surface, and we can decide whether we're going to break the solid into a series of discrete solids which are separate entities from one another. I'm just going to show that in the model browser tree. So making a simple split based on the face of the bounding box, we can see in the model browser tree we now have two new solids created. So if we were to mesh based on that definition, there would be no mesh congruency or nodal equivalence at those solid interfaces. So we're going to redo that process, but this time we're going to partition the solid about those faces, which breaks the solid down into, again, discrete regions or discrete partitions, but in the model browser tree we can still see a single solid under the 3D rib definition. So this gives us the ability to locally control the mesh density in a given partitioned region without having to use that mesh density everywhere within the rest of the model. So again, a couple of splits to break this solid down, and the dotted lines show the transition at the partitions. So again, a single solid but split into again underlying partitions. So we can now go into the solid mesh again and then look at different controls or different element edge lengths for discrete regions. So this particular partition, we're putting an edge length of 3 millimeters, and you can see very fine definition. We're going to use a slightly, well, double the size at the transition region, so 6 millimeters, and then we're going to go back to the original element edge length, so 12 millimeters for the rest of the structure. So just running through the set mesh algorithm for the larger rib, so it takes a little bit longer to do that. But again, because these are partitions, the mesh is the mesh understands the interface between local partitions and transitions the mesh accordingly. So you can see the mesh is tied together nicely, and if we looked at the element quality, we should see in the region of interest, yeah, we've got very good quality. We've got no bad, no invalid elements for the full extent of the rib, and we're dominated by good quality elements at the region of interest. So we look at the poor elements, yeah, there are no poor elements in that local partitioned region, so we've got good quality everywhere where we want to take results from, potentially within the model. Okay, so turning the element quality off just for a moment, and then we can use, again, the turning the solid geometry off, we can look at the mesh topology edges. So we can see we've got shared edges effectively where the element corners, where the elements make up corners. Obviously in the fillets there's no discrete corner as such because you've got a nice flow of elements, so the green lines don't show up for a much finer mesh density or description. But yeah, a very quick way of controlling the master mesh and the underlying partition sizes to give us the transitions exactly as we require them. So one thing we may be interested in is some means of assessing whether we have converged stresses in this region. So again, because we've got the partition set up, we can locally remesh one partition whilst maintaining the mesh in the other region. So we've halved the element edge length from 3 mil down to 1.5 mil in this particular example, this region, and maybe a bit of overkill. But what this demonstrates is that we can look at different mesh densities to show different effects in terms of the output stress and demonstrate convergence accordingly. So just a quick snapshot there in terms of what that means, but very quickly controlled. So moving on to the final rib definition. So this is looking at hybrid modeling or meshing techniques. So rather than partitioning the rib in a manner that we looked at in the tetrahedral mesh example, what we're going to do now is physically break out a portion of the rib structure, again at a region of interest, and we can use different modelling or different meshing techniques for the broken out portion based on the underlying geometry. So just in the model browser tree, changing the colour of the new part that's been cut out of the original rib, I should say. So you can say we've now got two parts in the model browser tree. So focused on this particular region. So we're going to highlight some of the hexahedral or hex mesh techniques. So this is all based on mappable geometry. So there's a tool within Apex we can see which colours the underlying geometric definition based on whether it can be hex mesh. So we turned that on then, and it showed the overall structure shown as red, which means it can't be hex meshed, and the hex mesh tool, if we tried to use it, would say sorry, it's not appropriate for this level of geometry. So we're going to make some splits in this underlying CAD definition, or 3D definition first of all. So we're going to split across the back face so we can chop out the fillet region to give us, hopefully give us hex meshable geometry or mappable geometry. So we're going to create some surfaces that extend between the fillet edge and the projection of that fillet edge on the back surface of the geometry. And again, the filler surface. So we're doing all this off the mouse, so selecting and accepting using the left and middle mouse buttons. And then, so once we have our surfaces defined, we can then split the solid geometry. So again, we're going to split using faces, and we're going to partition the solid. So we're not physically breaking off a new solid, we're just going to give us a partition for that region. Middle mouse button to accept, and the surface, or the solid is split. And then if we show the mappable geometry, you can see that new partition that's been split off is green, which means it can be hex meshed. So we repeat this process for the remaining geometry based on, in this case, splitting planes rather than surfaces. So studied this geometry a little bit, but know that we can basically split about a couple of flat, or a number of flat faces or flat planes, to break it down into the geometric representation. So second split there, we can see we're still not mappable for this lower portion, but if we start to split in a sort of chordwise fashion now, as we make these splits, the geometry becomes mappable. And again, just making sure we pick the appropriate vertices. You have to be careful not to pick edges near vertices rather than the vertex explicitly. So those breaks now, we're chopping out the fillet from the overall solid. So effectively we now have more and more partitions of the structure shown in green as opposed to red, which means they're now mappable and we can hex mesh them. So this is just a simple technique of breaking up the solid to give us the hex mesh that we require. Just a different approach to the tech mesh algorithm that we looked at in the last example, but a useful technique if you are maybe looking at models with trying to optimize the number of nodes. So a hex mesh can be a lot more efficient than a tech mesh in terms of the number of nodes or the size of the model required to capture specific detail in a given region. So this may be for some kind of downstream nonlinear analysis, or it may be for just simply to keep the model size down to a sensible level. So we've made those splits now based on surfaces and planes, and we now have a fully hex meshable geometry. Perhaps not the most complex example in the world, but it shows that we can do this very quickly. So theoretically we could have broken the full rib down, including the fillets, into a hex meshable definition, but that would take a bit more time. So again, using a 2.5mm element edge length, and you can see we've got the hex mesh mapped to to respect both the fillets and the underlying hole definitions and thickness through the solid sections. So just a quick sweep mesh in terms of the hex mesher. What we can do is we can use the 2D surface mesher as a surface seed to control the underlying hex mesh. So a couple of these faces where we saw potentially skewed elements. So with those seed surfaces or seed meshes defined, we can go back in to the 2D meshing, repeat the hex meshing process, and then we can double check the mesh as required. So just playing around with some of the display controls. So just going back into a 3D display, we can see we've got a really nice hex mesh definition, and we'd have a significantly smaller node count to capture that set of features than we would with a tetrahedral model definition. So we've got that region of interest hex meshed. So we've now got the original or the portion of solid which we cut out originally, and then we can go back into the original TET meshing algorithm. So just bring a simple sweep mesh based on a much larger element edge length across the structure, and you can see a bit more work for the TET mesher to do, because this is a much bigger region than the underlying hex mesh area. And you can see that the mesh is developed. Again, we've got feature mesh settings for fillets and washes around holes. Then once we have those two mesh types set up, of course they're not connected in any way through mesh transitioning or equivalent nodes. So we're going to use something called glued contact in Apex, and we'll be there are a number of tutorials available on glued contact. We'll run some specific ones in terms of this Aerospace 101 for, or rather Apex 101 for aerospace applications. But what we're going to do is create an assembly and drop the larger rib and the smaller hex mesh region into that assembly. I'm going to rename the move, and then rename the local rib detail, but where we've got the hex mesh. Just typing the name into the tree, we can see we've got that definition, and then simply in terms of glue, we just pick the two or more sets of entities we want to glue together using default settings in this case. And then effectively what Apex does, it looks at the boundary and develops internally a series of constraint equations which allow the two meshes to work together across that dissimilar nodal boundary. And if we just look at the glue on its own, and we can see those two interfaces are mapped very nicely at the transition between the coarse and the finer mesh. So we can run through the analysis, and again this would run through far more quickly than the full detailed TET mesh representation, and we can look at the displacement transitioning across the interface. You can see we've got a nice smooth definition in that region, and then we can post-process specifically on one of the regions, so in this case the rib detail, so taking out the larger rib from view, so simplifying the output and making the stress assessment more simple, more easy to understand. And then looking at the discrete output, so we've got von Mises shown by default, but perhaps changing that to max principal, so maybe interested in fatigue response or crack propagation. So we can look at the fringe or the discrete vectors, and we can put a hotspot display on to show where those peak stresses are and what values they're shown to be. And then we can start to make assessments on the underlying mesh quality and whether we've got stress convergence by looking at the unaveraged element results. So this is just the plain value for a given element, and then the discrete difference plot, which shows the jump from one element to the next. So we can look at these figures to understand how appropriate our mesh density is for this given type of region. So very quickly, one of the reasons why we spend time chopping up geometry to make it hex meshable is that there's a huge decrease in node count for a given structure, and we can see in this simple example that we're looking at that with those changes made to the hex mesh, we can have a much smaller model, but very clear distinction in terms of how the structure is going to work. Okay, so thanks for listening to this tutorial, and keep an eye out for more Evotech Apex specific tutorials.